So how do we actually find numbers for this? Equilibrium constants are going to depend on the temperature. So the temperature could be specified in the problem or in a description, but it doesn't become part of the equation. The concentrations, I told you we'd talk about what those units are. The concentrations are always going to be in moles per liter. Okay, that's a concentration that we haven't really talked about, and yet we know what moles are and we know what liters are. So it's how many moles of that substance are in a liter. Because we're interested in how many particles in a given volume. So we always use moles per liter, but we leave the units out of these equations. And the reason for that is, for different equilibrium expressions, we would end up with different units. We could end up with liters squared per mole squared, which is ridiculous. It's not meaningful. And so what we've decided to do is just have all the equilibrium constants have no units. So you should be happy about that too, because here's the one situation where I'm telling you, you can leave the units out, okay? So what's important to understand is that the concentrations will not always be the same. You could have the same reaction, just two different amounts that you started with, and the concentrations will not be the same. But the equilibrium constant is always the same. That's why it's called an equilibrium constant, because it doesn't change. So let's look at this reaction. We've looked at this one before. Hydrogen and iodine reacting to form hydrogen iodide. So let's just say that a mixture of hydrogen and iodine is allowed to come to equilibrium at 445 degrees Celsius. It's like, okay, well, that's very nice. We don't need to use that, though. The measured equilibrium concentrations are, so the concentration of hydrogen is 0.11, and so this capital M, we'll learn about that in a chapter coming up very soon. Capital M stands for moles per liter. That's all. We don't have to worry about it. And iodine concentration is 0.11 moles per liter, and the hydrogen iodide concentration is 0.78 moles per liter. What is the value of the equilibrium constant? So what we need to do is we need to write the equilibrium expression and then put these numbers into it and do a little bit of math. So we write the equilibrium constant, we write the equilibrium expression, the product, HI squared, over the first reactant and the second reactant. They both have coefficients of 1, so they don't have an exponent. Now we're going to take the numbers that were given. For HI, that's in the numerator and it's squared. HI is equal to 0.78, and we're going to leave the units off for a change. 0.78, and that's squared. Divided by the concentration of hydrogen is 0.11, and that's multiplied by the concentration of iodine, which also happens to be 0.11. I knew I forgot something. I forgot my calculator. It's okay, because I have a phone. Not as good, but it still works. So when you're doing this, again, we're dividing by two different things, so be careful with that. So 0.78 squared divided by, now open the parentheses, 0.11 times 0.11, close the parentheses, and press equals. My calculator cell phone is showing me 50.28 and a bunch of other digits. Did I do that correctly? How many significant figures should that have? Should have 2. All of those concentrations had 2 sig figs. So if I'm going to round this to 2 sig figs, I could call it 50 with a decimal point, or 5.0 times 10 to the 1. It doesn't have any units. The equilibrium constants are unitless. Any questions? Yes?
So the temperature doesn't really matter in this case? Or
The temperature does not come into the calculation at all. It matters, it does matter because the equilibrium constant we're calculating here is at 445 degrees Celsius. If you did the same experiment at 100 degrees Celsius, the equilibrium constant would be different. It would be a different number, okay? Because the equilibrium is affected by temperature. So you'll often see a temperature given. You actually don't have to pay any attention to it. Yeah?
So the numbers is kind of, well, the temperature is kind of all the degrees, please.
Right. If this was a different temperature, depending on the specifics of the equation, it might be that the reactant concentrations would be higher and the product would be lower, or vice versa. But we can't really tell. What we're doing here is we're introducing you to these ideas, but we're trying to stay right at the surface of the water. We're not going down where the sharks are. Yeah. Any other questions? So here's an example from your textbook. I thought this was a really useful table, but they didn't include it digitally in all of the instructor resources. So I took a picture of the book and put it in my PowerPoint. How fancy, right? So here, this helps us to understand what's going on here. So we just did that calculation where at equilibrium, we had 0.11, 0.11, 0.78, and we get an equilibrium constant of 50, which should have a decimal point. What if, so that was starting with half a mole of each reactant and no product. What if we started with no reactants and half a mole of product? Well, then we'd have the reverse reaction occurring until there were some reactants, and then we'd have some forward reaction. And eventually, we get to this point where we have 0.055 moles of each reactant and 0.39 moles of product. Where do those numbers come from? You might be wondering. Well, you actually have to do the experiment and measure the concentrations. And that's actually a lot more difficult than it sounds. But that's where in the video they talked about getting your hands dirty, right? You have to actually do something. So we measure this, and if we plug these into that equation, we come up with the same constant, still 50. If we start with equal moles of hydrogen, iodine, and HI, and let it come to equilibrium, and measure what those concentrations are after they've all equilibrated, plug those in, we still get a constant of 50. What if we start with twice as much hydrogen as iodine and no product, let it go to equilibrium, we end up with these numbers, we still get an equilibrium constant of 50. Get the idea? The equilibrium constant is constant. Doesn't matter what concentrations you started with, the constant will be the same at equilibrium. The concentrations of each of these things is not the same in these different examples. But when we put them into this relationship, they all give the same number. You see it? Any questions? Well, let's do another example where we calculate an equilibrium constant. So here we have this reaction, carbon monoxide and hydrogen forming methanol. So we've got this mixture, and we allow it to come to equilibrium at 225 degrees Celsius. Like that's just like, they're just telling us that, and we're like, oh, okay, thanks. I don't need that, but there it is. We don't need to use that at all. The measured equilibrium concentrations are blah, blah, blah. What's the value of the equilibrium constant? So we write the expression, and then we put the numbers in and calculate the constant. So KEQ equals, we've got the reactant on the bottom and the product on the top. So CH3OH, the concentration of that. When we put brackets around a chemical formula, what we're meaning is the concentration in moles per liter. That's going to be divided by the concentration of the carbon monoxide and the concentration of the hydrogen squared, because it's got a coefficient of 2. Then we're just going to take the numbers that are given and put them in. Make sure you match them up correctly. So CH3OH is 0.151. So that's in the numerator. And then in the denominator, we've got the CO, 0.489. And we've got hydrogen, 0.146 squared. So get out your calculator again. Be careful with the denominator there. 0.151 divided by, now open the parentheses, 0.489 times 0.146 squared. You should have an x squared button on your calculator, or you can just punch it in twice, which is what I'm doing on my Lamo calculator, cell phone calculator. And I'm going to round this to 3 significant figures. I'm coming up with 14.5. Did I do it right? Yeah? Okay. Any questions? We can use this equilibrium constant to predict what the concentration of one of the reactants will be at equilibrium. And this is the real usefulness of the equilibrium constant. So if we have this reaction occurring, we've got COF2, and that will decompose and form carbon dioxide and carbon tetrafluoride. The equilibrium constant is 2.0 at 1,000 degrees Celsius. So 1,000 degrees, fine, it's just there. We'll ignore it now. This equilibrium constant of 2 is approximately 1. That's pretty close to the number 1, meaning there's going to be significant amounts of reactants and products. So they're giving us the concentration of COF2 and of CF4. We know what the equilibrium constant is. They're asking us this time, what's the concentration of CO2? So what we're going to do is we're going to write the equilibrium expression again. We end up writing these equilibrium expressions a lot. So it's the products, they're all gases, so we have to include everybody. We've got CO2 times CF4 divided by the reactants, COF2. That has a coefficient of 2, so it's squared. Now there's 2 ways that you can approach this to find out what the CO2 is. You can stick the numbers in and then mess around with calculating and rearranging. I don't recommend doing that, so I'm not going to do it in lecture because students make horrible messes of it. I think it's better to rearrange it while we've just got letters and then plug the numbers in. So again, we have an equation here with a fraction, and that screws a lot of students up, so let's first cross-multiply and get rid of the fraction. So KEQ is the same as KEQ divided by 1, right? So cross-multiplying, I'm going to have KEQ times this being equal to 1 times all of that. So I'm going to get, let's see, I'm going to start over here. KEQ times COF2 squared is equal to CO2 times CF4. I got rid of the fractions. Now it's easier to see what do I need to do to solve for CO2. I need to divide by CF4. So I'm going to divide by the concentration of CF4 on both sides. So CF4 over CF4 is 1. And so I'm going to divide by this over here. And now I have the concentration of CO2 is equal to this. Any questions? I know some of you are still having some trouble rearranging equations. Please come and talk to me. I can help you with that. So I'm running out of space, so I'm going to cheat a little bit. So there's my equation. I just neatened it up a little bit. Now I'm going to plug the numbers in. So KEQ is 2, and COF2 is 0.255, and that's squared, and that's divided by CF4, 0.118. And we're just leaving units off. We've got 2 times 0.255 squared divided by 0.118. This will have 3 sig figs. I'm coming up with 1.10. Now that's a concentration. The concentrations all had units, and the unit was capital M, which stands for moles per liter. Any questions? So KEQ doesn't have units. We ignore the units when we're doing the calculations, but then at the end we have to put our thinking caps on and say, oh, this is the concentration. I'm going to slap the unit back on there. Let's do one more. Diatomic iodine decomposes to form iodine atoms. We're given a balanced chemical equation. We're given the value of KEQ. We're given a temperature that we don't need. And we've got a concentration of I2 of 0.10. So it's asking, what's the concentration of I? So we'll write the equilibrium expression, KEQ. Products, the product is I, and that's squared over the reactant, which is I2. We're trying to find the concentration of I2. So if we cross multiply to get rid of the fraction, we're going to get KEQ times I2 equals the concentration of I squared. Well, that kind of worked out nicely, right? We want I by itself. Here we've got I by itself on one side of the equation. But this isn't just I, it's I squared. When we rearrange to solve for a variable, you undo functions by doing the opposite. If there's multiplying, you divide. If there's a square, you take the square root. If I take the square root of both sides, it's okay as long as you do the same thing to both sides, you can do whatever you want. The square root of something squared is just itself. So there we have the concentration of I. Then we put the numbers in. So the concentration of I equals KEQ 0.11 times the concentration of I2, 0.10, and then we need to take the square root of that. So I want, where is it, the square root. It depends on how your calculator works. This one is wants me to do the multiplication first and then do the square root. So I'm coming up with 0.033. Anybody else get that? Okay. When you're doing square roots and stuff, then significant figures get a little weird. We're just not going to worry about it. Any questions?